Our universe is a very dynamic place that puts on spectacular cosmic displays every second. With Roman's panoramic vision, we'll not only catch these events, but we'll see many at once. And use this to uncover the distribution of dark matter in our universe. Most of the sky remains to be explored. We're likely to not confirm current models, but to get to explore entirely new phenomena for the first time. I think when you build an observatory that has profoundly new capabilities, the most exciting science is going to be the thing that you didn't expect.
Hello and welcome to NASA's Kennedy Space Center on Florida's Space Coast. Thank you for watching the Science News Conference for NASA's Nancy Grace Roman Space Telescope, a mission that will transform our view of the cosmos. I'm Claire Andrioli with NASA's Office of Communications. We are just one day away from a moment years in the making. Roman will explore some of the universe's biggest mysteries, from dark energy and dark matter to planets beyond our solar system. Today, I'm joined by a panel of experts to give you a broad overview of Roman's science. Shawn Domagal-Goldman, Director of NASA's Astrophysics Division, NASA Headquarters. Julie McEnery, Roman Senior Project Scientist, NASA's Goddard Space Flight Center. Vanessa Bailey, Roman Coronagraph Instrument Scientist, NASA's Jet Propulsion Laboratory. Kristen McQuinn, Roman Science Operations Center Lead, Space Telescope Science Institute. And Lee Armas, Roman Science Support Center Lead Scientist, Caltech IPAC. Thank you to everyone for joining. We'll begin taking questions right after opening comments from our mission experts. Those of you watching online can submit a question at any time by tagging @NASA. And now, to start our discussion, I'll kick it over to Shawn.
Thanks, Claire. I am really, really happy to be here today to talk to you all about the Nancy Grace Roman Space Telescope and about two incredible things that are happening in this room right now. The first of those is not unique to this room. In fact, it's happening in every room on the planet right now, in every corner of the solar system, and frankly, all the way out to the outer reaches of the universe. And that is the expansion of the universe itself. It's expanding over time, and that expansion is accelerating. It's getting faster. And when we bring the brightest minds together, we write down equations to explain that behavior. And as you'll hear about in a bit, there's starting to be cracks in our understanding of that process. And that's one of the fundamental cosmic mysteries of our time. It's called dark energy. There's another cosmic mystery called dark matter, which is matter that we can detect the presence of, but we cannot see. But we don't know why it's there or what it's doing in the universe, but it makes up most of the universe that we inhabit. And a third mystery of are we alone? To solve that one, we both need a good census of the Goldilocks zone, or of the places around stars that are not too hot or too cold to harbor life. And we need to complete that census while we build the technologies to go look for signs of life on those habitable worlds. Those cosmic mysteries are things that we have designed a specific scientific experiment to help us address. That's the Nancy Grace Roman Space Telescope. That's a telescope with the precision of Hubble, but a field of view 100 times bigger than Hubble and the ability to tile the sky 1,000 times faster. That's going to give us the capability to bring down the data that global scientists need to answer those fundamental cosmic mysteries I spoke about before. But with those data, the huge reams of data, comes a separate challenge. How do we make sense of it? All those numbers. To do that, we've assembled a teams of experts. And that's the other special thing happening in this room today. And that's unique to this room, because you're going to hear from people that are technical experts in their own rights about these cosmic challenges. And you're going to hear about how they're leading teams of technical experts to help bring those data down and disseminate them to the world so that the smartest minds from across America can help us figure out what we're doing in this universe. And the person that's led this team of teams is Dr. Julie McEnery, who's speaking next.
Thank you. So I can honestly say I am completely thrilled to be here. Roman is poised to conduct extraordinary surveys that will impact every area of astronomy. We'll perform a revolutionary census of planets around other stars and may confirm that our standard model of the universe is incorrect and put us on the path to figuring out what is right. And we can do all this because Roman's primary instrument combines exquisite performance and sensitivity with the ability to efficiently and quickly cover large regions of sky. It starts with our field of view. At any instance, Roman will see more than 100 times the amount of sky that Hubble can see. But it's more than that. Roman will move and stop and be ready to take the next image very quickly. So it can survey the sky more than 1,000 times faster than Hubble. So to put this into context, a survey that would take Roman 1 month would take a century with Hubble. So Roman doesn't do Hubble science faster. It addresses entirely new, ambitious science questions, while Hubble continues to do the great things that Hubble does. That 1 month of Roman observations could survey our own Milky Way galaxy, resulting in the detection of up to 20 billion stars. That would itself represent a catalogue of astronomical objects much larger than any in existence today, with just 1 month of Roman observations. Our main survey will take over a year and be really huge. We would need over 500,000 4K TVs to fully display the single Roman image from our largest survey. And I don't know about you, but I don't have a feel for 500,000 4K TVs. It would fully cover 45 Manhattan city blocks, or entirely cover El Capitan in Yosemite National Park. But I don't think we should actually cover El Capitan, because that would be bad. This survey will contain over 2 billion galaxies, and it will enable us to study how the structures in our universe, the stars, the galaxies, the clusters of galaxies, grew and evolved. We'll also measure how our own universe has expanded over time, measure the acceleration that Shawn recently described. And these are the keys that will allow us to unlock the fundamental nature of dark matter and dark energy and the fabric of the universe itself. Our universe puts on spectacular cosmic displays every second, but they happen very quickly, so they often elude our telescopes. With Roman's panoramic vision, we'll not only catch these events, but we'll see many at once. We'll identify tens of thousands of supernovae and use these as markers to track the expansion of the universe. We'll detect bright flares as a star is swept into a supermassive black hole. We'll see the extraordinary outbursts when 2 neutron stars merge to form a black hole. And these studies are even more exciting now, the studies of the universe. Recent observations hint that our standard model of the universe is incorrect. Roman will be able to confirm this and provide the data needed to explore the new phenomenon. So it's incredibly exciting. We're likely to go beyond standard models and explore entirely new phenomenon for the first time. Periodically, we'll set our sights towards the center of our own galaxy and monitor hundreds of millions of stars every few minutes. But we're not only going to be measuring millions of stars, we're going to be discovering a host of new exoplanets, up to 40 times more than are known today. So think of this as the largest census we've ever done of other planets in our galaxy. Roman's vast reach will allow us to find the weird, the rare, and the unusual. Discovery of things like exoplanets with disks, isolated black holes and neutron stars in our galaxy, and runaway supermassive black holes will become routine. We'll redefine what it means to find a needle in a haystack. Extraordinary observations generate extraordinary amounts of data. We've already collected, just in our test campaigns, more data than Hubble and Webb combined. This has driven a new way to use the data in the cloud, where users access and use the data directly. Our data are immediately available to all, so a high school class in Kentucky can access new Roman data at the same time as a professor in Princeton. What makes me most excited about Roman is the discovery potential. With 2 billion galaxies, we'll have 2,000 objects that are 1 in a million. We'll be exploring patches of sky as a function of time with exquisite sensitivity. We'll find new things that go bump in the night. I very much hope, and in fact expect, that the most exciting science from Roman will be a surprise, something we couldn't predict, and that will set the stage for the next deeper set of questions for future missions to address. But there's more. We have a second instrument. And my colleague, Dr. Vanessa Bailey, will tell you all about that.
Thank you. Yeah, I'm very, very excited to be here, and thank you all for being here as well. So now from the very wide to the very narrow and the very deep with the second instrument on board Roman, the Coronagraph instrument. We'll get to why it's called that in a minute. So maybe you've seen this first image here. When the Voyager spacecraft turned around, looked back at Earth, and saw what Carl Sagan called the pale blue dot. So it may surprise you to learn that astronomers have already taken pictures of planets not only in our own solar system, but around other stars as well. We can't yet take pictures like this of Earth-like exoplanets, but that's one of NASA's most ambitious long-term goals. And Roman will help set the technological foundation for that capability. So if you try to imagine seeing an exoplanet next to its star, it's going to be very challenging. The starlight is going to be overwhelmingly bright. It's like trying to see a firefly next to a lighthouse hundreds of miles away. We can use a technology called a coronagraph inside of our camera to block that lighthouse and see the firefly. With today's observatories, as you'll see in this next image, including the Hubble Space Telescope and the James Webb Space Telescope, astronomers already use coronagraphs to view hot, young, glowing superjupiters in the infrared. These planets are only 1 million times fainter than their stars. These are the fireflies. You're seeing one example here in this image from the James Webb Space Telescope. One day in the future, NASA hopes to detect an Earth-like planet in this way. That little Earth twin would be 10 billion times fainter than its star in visible light. And that's 10,000 times better than what we can do today, which is just too great a leap to make in a single generation of instrumentation, no matter how bright your engineers are. And that's our purpose as the Roman coronagraph, is to be that intermediate stepping stone. We think that we will be capable of detecting exoplanets that are about 100 million times fainter than their stars. And with that capability, in the next image, we are hoping to see our pale brown dot instead of a pale blue dot, a Jupiter twin around a nearby star using visible light reflected from its cloud tops for the first time. And then we can use that light to study the composition of its atmosphere. We're also going to do, I hope, some detective work about how planets form and evolve. So just like an archaeologist looks at the remnant buildings and belongings to understand an ancient civilization, we're going to look at the rubble, the asteroid belts and the debris disks, to search for clues to how the planetary systems formed and evolved. And the question, of course, is how do we do all of these incredible new observations? What technology do we use? Well, we build not only an instrument, but also an observatory that work together in concert. So inside our instrument, we use something called a coronagraph to block the starlight. That's our namesake. It's a bit like how on a bright day you hold up your hand to block the sun. Maybe if you're here in person, you're going to be doing that tomorrow morning during lunch if you're looking east. And in fact, more than 100 years ago, astronomers used coronagraphs to create an artificial eclipse to study the sun's corona. That's the reason for the name. We've since adapted it to block light from other stars to see the faint planets orbiting around them. And Roman is not the first NASA mission to fly a coronagraph, but we are the first to fly what we call an active coronagraph that you'll see in this animation here. We've added so-called deformable mirrors that can bend and flex and correct for the most minute polishing or misalignments, errors in the system that would otherwise cause starlight glare and obscure our exoplanets. These deformable mirrors are a real engineering feat. They can be commanded with the precision approaching the size of an atom, and this is what really allows us to make this transformative performance leap. That's not all. There are various other key technologies in the instrument, like exceedingly sensitive detectors and exquisite temperature control that truly were engineering feats in their own right. And even the best deformable mirrors couldn't compensate for an unstable telescope. And luckily, we're on board Roman that's an exquisitely stable observatory. All of these pieces will need to work together as one system. That, in fact, is our primary purpose, to demonstrate these technologies together. at the same time, we're going to do a lot of really exciting science. And all our data will be public. And I'm very happy to pass to Dr. Kristen McQuinn to tell you more.
Thanks, Vanessa. So the role of the Science Operations Center for Roman at the Space Telescope Science Institute is to both support the observatory and help turn Roman's observations into science. STSCI is a NASA-funded institute with a long history of serving NASA's flagship observatories, the Hubble and James Webb Space Telescope. And for Roman, we continue that work, and we're focusing on 4 main areas. First, we plan for and schedule Roman's observations for the 5-year prime mission. More than 1,000 scientists contributed to help define what Roman needs to observe in order to answer some of the biggest outstanding questions in modern astrophysics. What's the nature of dark energy and dark matter? How did our Milky Way come to be, and how many Earth-like planets are out there? At STSCI, we take the high-level plan defined by the scientific community, and we translate that into a detailed 5-year observing plan. I like to think of this as planning, your dream vacation. You've always wanted to take a tour of Europe, and now you finally have the chance to do it. And you have to plan your detailed itinerary, taking into account train schedules and museum hours and budget constraints. It's complicated. Planning Roman's 5 years of observations all at once is similar to planning the vacation of your dreams, except at a much larger scale and with very, very complex technical constraints. Second, we process, archive, and make accessible Roman's data. Roman will generate an extraordinary amount of data and information about our universe. Realizing the scientific potential of that information means that we need to transform the raw starlight that's captured by the telescope into science-ready data. So at STSCI, we'll be receiving the data to process it. And I think about this as similar to taking thousands of photos on your phone every day. And before you want to share and post it, you want to make sure the light is balanced, that imperfections are removed, and that maybe you've tagged every person, event, or pictures of your cat before you make them searchable. So we're doing that for Roman. We'll receive thousands of images every day. We'll calibrate them, align them, make them searchable, and make them accessible to everyone in the world on timescales of about a day. We're also working to make access to and exploration of Roman's data easy and intuitive, which is really important to accelerate science. Traditionally, astronomers would download data onto their laptop to analyze. Roman's data is too big to do that. So instead, we've built a cloud-based digital workspace called the Roman Research Nexus, where researchers can log in through a simple web browser and analyze any part of Roman's 20,000 terabytes of data. This is a major shift for the way astronomical research is done, and I think it's a little like the evolution of watching movies at home. Back in the day, we would rent movies from Blockbuster to take home, for those that remember that. And then later, we had DVDs mailed to us by Netflix. And today, we have streaming services that bring the content right into our home. We're also developing the capabilities to allow scientists to easily explore Roman's huge images, while also quickly being able to find specific types of planets, stars, galaxies, or cosmic structure for deep analysis. This is a little like the functionality of Google Maps, where you can see the entire world, you can zoom into a local neighborhood, you can search for a coffee shop near me, and then you can order your custom cup of coffee online. We also work to train the scientists on how to use this new observatory. Every major telescope has a steep learning curve. And Roman's not just a new observatory, but it introduces this new approach to interacting with astronomical data at scale. So we train the scientists, we support them. We're also a hub and a gathering place for scientists to come. We can share our expertise with the broad community. And along with our mission partners, our scientists, engineers, and technical experts are ready to build the bridge from Roman to the astronomical worldwide community. And we're also really excited to watch the mysteries and discoveries unfold from Roman, and to participate in Roman bringing a new view and a deeper understanding of the universe to us. And now to Dr. Lee Armas.
Thank you, Christy. Good morning, everyone. My name is Lee Armas. I'm the lead scientist at the Roman Science Support Center at IPAC. IPAC is on the Caltech campus at the California Institute of Technology. We partner with NASA, the NSF, JPL, and the research community to advance the exploration of our universe through science operations, data archiving, community support, and engagement. At IPAC, we have experts in cosmology, galaxy evolution, exoplanets, solar system science, time domain astrophysics, and infrared astrophysics. We've supported over our 40-year lifetime more than 20 missions, and we're extremely excited to partner with Space Telescope Science Institute and the Roman Project to bring the Science Center functions to the entire astronomical community. So I thought I would review a few of the responsibilities that we have for Roman at the SSC. First, we have the design and implementation of the science data pipelines for wide field spectroscopy and the galactic bulge time domain survey for the wide field instrument. So besides taking exquisite, highly accurate pictures of the entire universe, Roman also takes spectra, where we break up the light from every single object in the entire field of view into its constituent colors to provide a fingerprint of every single star and galaxy in the field of view. So for one of our high latitude surveys for Roman, we should be able to get spectra for more than 10 million galaxies, just like our Milky Way, when the universe was less than half of its current age. And that's when it started accelerating, and that's going to provide everyone with a 3D map of the universe at the time when dark energy became very important. From the Galactic Bulge Time Domain Survey, we're going to monitor more than 200 million stars and find thousands of exoplanets. Besides the science data pipelines, I wanted to mention that we do at IPAC, that we pick up the exquisitely calibrated data from the Space Telescope Science Institute. We process it further to produce those spectra, to find those exoplanets, and then we pass it back to the archive for the entire community and the public to use. We also support the planning and operations of the Coronagraph instrument on Roman that Vanessa was telling you about. We manage the community proposal and peer review process for Roman observing time and data analysis funding. We recently had a very successful Cycle 1 call with more than 350 proposals came in from the scientific community for more than 2,300 investigators from 15 countries. The entire world is extremely excited to use Roman and get to the science for Roman. Finally, we also engage the community, the astronomical community, and the public about Roman spectroscopy and exoplanet science. And I'd like to thank you all for being here today and say we're extremely excited about participating in Roman, and go Roman.
Thank you so much to our experts. We will now begin taking questions. For those in the room, just raise your hand and we'll get a mic over to you. And for those on the phone, please press *1 to get into the question queue. And we'll start over here, gentleman in the middle. Yeah, with the jacket right there.
Good morning. Jeff Faust, Space News. On the Coronagraph, I'm curious how its observations will fit in with the survey work. I think you've got a certain amount of time during the first year or so to dedicate to observations, but how will that work in? And then in the future, once the technology has been demonstrated, how will it be available for some of these other work?
That's right. So the Coronagraph instrument has an allocation of about 2,000 hours of observing time spread over the first 18 months of the mission. We'll interleave our observations with those of the various surveys that Julie was telling you about, because we're looking at the narrowest of soda straws. We're pointing at star by star by star, rather than taking an expansive survey. So Roman has two sides to it, basically. And we're going in our early operations at the beginning of the next calendar year. We're going to try to push as hard as we can, as fast as we can, to understand what the instrument and the observatory are capable of, and then plan an ambitious portfolio for the remaining 2,000 hours after that. The pathway, you asked the pathway to get involved. We have a community participation program of scientists from the U.S. and our international partners, and they hold white paper calls and community engagement events so that we can be sure that our observations are representing what the community most wants to see from Roman Coronagraph.
We're We're going to pivot to a question from the phone. We have Pablo Fuente with Radio El Respeto on the phone. If you want to go ahead.
Question. With the amount of data that can be downloaded, more than 1 terabyte per day, do you guys plan to distribute that data among teams around the world to focus on specific areas of discovery? Thank you.
I know the answer is yes.
Well, so
many
actually,
of you could go into more detail on that.
So the answer is yes, but so the as the data are downloaded, it goes straight onto the cloud. So we don't have a model of distributing physically to multiple different archives around the world. That may happen in the future if somebody wants to do a very compute-intensive AI study of the data. But our current baseline is that there's a single entry point in the cloud and that people have, all go to the data. So in that sense, it's not really sent out to separate teams, that everybody is accessing the data in the same place at the same time, and that time is immediately that they're processed. So it really doesn't matter if you're in Spain or in Baltimore or in the high school in Kentucky.
And I'll add to that we've also added capabilities in this cloud-based infrastructure, that it's not just one scientist that can log in and do analysis on the data. Scientists can log in as teams, and so they can share files, they can share the compute resources, they can simultaneously run analysis together. And so we've created a collaborative environment in this platform that really is meant to promote team science. Roman's data are so large that it really is going to take a village. And so we've designed this new infrastructure with that in mind.
We have one on the side of the room, black shirt.
Thank you. Manuel Masanti with Exploración Espacial. A question for Julie or Vanessa. I just want to be clear. So the wide field instrument and the coronagraph can work in parallel at the same time? Yes, you just say. Okay. I just wanted to see, I don't know if you needed to switch modes to coronagraph mode, or are you using the data of the wide field instrument in order to filter the light?
The wide field instrument is not only doing science. One of the roles of the wide field instrument is to provide the fine guiding for the observatory. So any science observation with Roman, the wide field instrument has to be operating. So when we're conducting coronagraph observations, I mean, obviously the nature of the observations are a little bit different to the kind of surveys that we would do with wide field, but we will be collecting data with wide field when we're taking coronagraph observations. And maybe Vanessa might like to say a few words about what's special about the mode of the observatory when we're doing coronagraph observations, because it's a little bit.
Yeah. I mean, I think you explained that very well. When we say using one instrument or the other, we mean who's driving. There's the other is a passenger. So we will observe very bright stars. We're choosing these bright stars because we expect to maybe either be able to see planets or that dusty debris around them. And then in order to achieve that targeted pointing at a specific star, the wide field instrument will be pointing nearby to align the telescope, and we'll get these serendipitous deep observations with the wide field instrument because the coronagraph needs to stare at a particular star for tens of hours.
There are wonderfully, delightfully random locations in the sky, so we have absolutely no idea what we're going to find.
On the side of the room, second row, third chair in.
Thank you. Irene Klautz with Aviation Week and Space Technology. For Julie, I realize that physicists spend their career answering this question, but in a nutshell, what is the problem with the standard model, and what are the theories as to why it's wrong?
Okay, so let's see if I can explain the universe in 30 seconds. So we make measurements of the universe at very, very early times with the cosmic microwave observations. And that tells us about the nature of the universe right, close to the beginning. And then we can use things like supernovae and the galaxy surveys to make measurements of the universe close to now. When we discovered that the universe was accelerating, which is completely crazy. I mean, it's like, you throw a ball in the air, instead of it coming down, it goes rocketing away. And it's as surprising that the universe behaves like that as it would be to you if that happened with a ball. So one of the simplest ways to explain how this happens is that there's a property of space-time that is repulsive. And the easiest way is to say that that property is constant. So we have a model that has constant, cosmological constant, dark energy is that constant property of space-time, that we have a good model for how we think dark matter behaves. We still don't know what it is, but we have a model for how it behaves. And that model is exquisitely good at taking the early observations and accurately predicting what we should see now. As our observations, as our ability to measure the expansion history of the universe, as our ability to measure the growth of structure in the universe, because of course matter clumps, and it clumps, the nature of the matter affects how it clumps. As we've started to measure those things more and more precisely, there's suggestions that maybe we don't have it quite right. The Hubble tension, which is the expansion of the universe now, is not quite consistent with what our models would have predicted. The expansion of the universe at early times is not quite consistent with what our models were predicted should be now. The structure is not quite what we predicted should be. And then, excitingly, there's been observations that have suggested that that dark energy, the cosmological constant, is in fact not a constant, and that it's varying with time. So that could mean that we have dynamical dark energy, that the properties of dark energy change as the universe expands. It could mean that we need to revisit how gravity itself works, that maybe our understanding of how gravity works on very, very large scales is in fact not well described by general relativity. What I'm sure of is that Roman's observations are going to definitively address at least some of those questions, because it will definitively say, yeah, the model works, or it doesn't. And if it doesn't, it's going to provide us with the precision and quality of data that will allow us to start to distinguish between those options. That was more than 30 seconds.
We have a question from social media. Manish on X asks, Roman is designed to investigate whether dark energy has changed over cosmic history. If Roman finds evidence that dark energy is not constant, how fundamentally could that change our understanding of the universe and its ultimate fate? Again in 30 seconds.
Well, this is actually very similar to the last question. So, if the acceleration of the universe is in fact slowing down and not continuing to accelerate, then that implies that we're not heading for a big rip. I mean, where everything expands so much that you're ripping atoms and particles apart. So I'll just say that it will give us the information that we need to figure out where it's going to go, but the options for what that could be are pretty wide open right now.
We now will take a question from the phone. We have a question from Marcia Dunn with the Associated Press.
Oh, good morning. Thanks. I'm wondering if someone can tell me when science observations will actually begin, given an on-time launch. I realize it'll take 100 days for the telescope to get to L2, but will the instruments be commissioned as it's traveling out there, or do you have to wait till it gets there? I mean, when can we expect the first science observation pictures? Thanks.
Well, I've got good news. We do not have to wait until we're out there. We will be turning on and commissioning the observatory and the instruments as we're on our journey to L2. We can start our science operations before we've actually inserted into our orbit at L2. We're planning to take 3 months to commission the instruments and the and the observatory. And that means, turn things on, make sure that everything's calibrated, collect the initial set of data that allows the pipelines to run. And then we'll start our regular science programming. So you can expect first flight sometime before the beginning of next year.
Front row, this side of the room.
Hi, thank you for doing this. Ken Kramer, Space Up Close. We're all very excited for you. I want to ask about the Coronagraph and the exoplanets, please. Tell us a little bit about how these deformable mirrors will operate. You're going to be looking at one star at a time or many stars at a time, and you'll be testing to figure out what is the best way to block out the light, and you'll be learning over time. Is that right? And talk a little bit about the atmospheres. What do you expect? Could you detect water and carbon and oxygen and things like that? Thanks.
Yeah, maybe I'll start with the second question first. Is the new type of object we hope to be able to see? If I'm being honest, it's right at the hairy edge of what we can do. Our most challenging hope is to see that Jupiter twin in reflected visible light. It's so small and so faint that for some of them we might only get a single image and not a spectrum. I hope we may, for one system, maybe two, be able to get a very low resolution spectrum, and we'll use that to look for methane in their atmospheres as kind of a proof of concept. We're not looking, we don't have the sensitivity to detect habitable planets or Earth-like planets, so we're still looking at the Jupiter-like planets. How we do that is with, yes, these deformable mirrors. They have about 1,400 pistons on the back of each, and we have 2 of them. We point at a very bright kind of tune-up star, and we observe the pattern of starlight glare in our science image, and we have a model that tells us from that particular pattern of glare what type of optical error it is, and we command the deformable mirrors to compensate. Our model isn't perfect, so we'll probably have to iterate over this several dozen times, but by iterating and learning as we go, we'll dig deeper and deeper on a given star.
I might jump in with an analogy that I'm wearing right now, the glasses on my face. I went to an optician, right? They measured my eyes, I measured my vision, and then they gave me a prescription, which I then mailed in, and they designed lenses to basically impart the opposite error that my eyes impart. What the Coronagraph does is it's basically doing that measurement and then reshaping the deformable mirrors, the lenses, like on a fast cadence to correct the vision that the telescope is imparting. And that's harder the less stable the telescope is. The other part of this equation that's really important is the telescope itself that we're getting on Roman, because of the precision we need for some of these cosmic mysteries, is also very stable, which it's stable enough for the Coronagraph to do the hard work on the back end of adjusting to whatever errors the telescope is imparting, and they operate as a system.
We'll go to the side of the room, front row.
Thank you. Chelsea Goad with Space.com. We're looking at dark matter, dark energy, the search for an Earth twin or Jupiter twin first. These are massive existential questions in science, but just generally for humanity. And I'm curious how you hope the general public will connect with Roman and these massive existential questions, how they will relate to it.
Sure.
Yeah, okay, I'll start. Yeah, I think this could be for anybody, but I think we all want to know if we're alone. We all want to understand our place in the universe. So I'm very excited for the exoplanet capabilities from this mission, that the Wide Field Instrument and its microlensing survey are going to help us understand how common Earth-sized planets are in that Goldilocks zone. This will be the first time we have that information. We're going to get so much closer to understanding whether we're alone. So for me, that's a big motivating question, and I think it may be for some other folks too. I'm sure others have opinions.
So I was pausing because I can't remember a time that I haven't been passionate to learn how the universe works. So I can't really. I struggle to imagine how to explain that. To even, I feel that well, I can't come up with good words for that, but I think that there's always something driving about exploring. I mean, the pursuit of knowledge for its own sake. I mean, whether it's, is there a continent on the other side of that ocean, or is there what is the nature of the universe beyond the horizon that we're currently able to see, or in some sense, some of the same kind of questions. I think that some of what we're going to do with Roman is going to be inspiring, and it's going to be inspiring not just for, I hope, not just for nerds, not just for scientists, but actually the country at large. And I think an important part of our job as scientists, where we have like the privilege to work on something so exciting, is that the onus is on us to convey what we're doing in a way that shares the excitement of what we're doing. I mean, it's something that I really passionately think that we do big, ambitious things, and everyone in the country should be proud of that, and everybody should feel that they're part of that. I realize it's not a very concrete answer, but like I said, I don't represent the person who is ever not excited about how the world works. So,
I think just the one other thing I would throw out here is we have a citizen science program at NASA as well. So for those that really if they're nerds like us and want to be a part of that journey, there's ways that they'll be able to engage not just the data, but even help find discoveries in the data sets. And this is going to be a citizen science engine. It's going to be awesome for them.
We have a question now from social media. Courtney on X asks, how was Roman able to launch 9 months ahead of schedule and under budget?
I heard a wonderful presentation from Jackie Townsend, who's our wonderful project manager, and she was the long-term deputy project manager under Jamie Dunn. And the two of them have had a consistent message, and I want to hear from Julie if she wants to add to this. But it comes down to a few things. One is you have to create a great team, because I don't care if you're the smartest person in the world, you can't do something like this, whether it's building the telescope or operating it on your own. You need, frankly, teams of teams. And so the first thing you got to do is you got to pull that team together. And then you have to make it a team. You have to have the openness and the honesty and the engagement both down and in to that team itself, and then up and out to stakeholders and leaders that are supporting the project. And I think we've had a history of just amazing leadership on this project, including on the science team with Julie and the team we've got here today to make that happen. And then the other thing is you have to make sure that you get the funding you need when you need it. And this project was fortunate enough to have that. It allowed the project managers to do everything that they needed to on a clockwork schedule. Folks like me and frankly my predecessors deserve a lot of credit for this, made sure that this observatory had the funding it needed on the profile that required to bring it to the launch pad on time and on budget, ahead of schedule and under budget. Julie, I don't know if you want to add to that.
I'll just add that there was a team spirit where people wanted us, when you're part of something that is successful, you want to keep that going. I will say that the team at large are quite happy that a few days ago we had our last daily 7 a.m. meeting. And I'll stop just right there.
We're going to take one from the phone now. Katrina Miller with the New York Times.
Hi, thanks so much. And apologies if this has been asked already, but can you clarify if the Coronagraph will be used to find new exoplanets, or is this sort of just like a proof of concept for looking at already discovered exoplanets? And I guess as a corollary to that, what can you dig into the details of the other planet finding techniques that will be used with Roman?
I'm sorry, you were a little bit faint. Would you mind repeating the second part of your question? If that's possible. Well, I can at least speak to the first part, and maybe somebody else caught the rest. But the question of is the Roman coronagraph trying to discover new planets or characterize ones we already know about? It's the latter, because this setup process, the tuning of our deformable mirrors, is a very time-consuming effort. So we want to only target those systems where we expect to see something. We'll use, there are other methods that can indirectly suggest the presence of a planet in a system, and then we'll go to characterize that specific one. Yeah, and I didn't catch the rest. I don't know if
I think it was around the discovery and detection techniques for Roman for finding planets, like microlensing and transiting.
Ah, okay. Do you want to take that? Do you want me to take that? You take it. Okay. Sure. So, so on the wide field instrument, we'll use two different techniques to discover exoplanets. The first one is called the transit technique. This is like Kepler used, like TESS used. When you have a planet orbiting its star, if the orbit is aligned just right, it will appear to pass in front of the star from your perspective temporarily, blocking a little bit of the star's light. The star will appear temporarily dimmer. If you see that happen multiple times, you can infer that it's a planet, and you can get the radius, the size of the planet from that observation. Roman is expected to detect maybe 100,000 new transiting planets this way, compared with the 6,000 plus. That's the total number of exoplanets we know today, which I find pretty astonishing. And with the same data set, they're going to use the so-called microlensing technique. Basically, a star's gravity bends space-time a little bit and can kind of act like a lens that can brighten background objects. A little planet around it would do the same thing. So with the same data set where you're monitoring the brightness of stars over time, if you see a little dip, that can suggest there's a transiting planet. If you see a little brightening, that can suggest there's a microlensing planet. It's the microlensing technique that will be sensitive to the Earth-sized planets in the habitable zone. The transiting technique is going to be most sensitive to planets closer to their stars. I don't know if you want to add anything, anybody?
One more thing, because it's related to some of the work that's happening at IPAC, which is the microlensing, which is the analysis of the data for the galactic bulge time domain survey that I mentioned, which is precisely using the technique that Vanessa mentioned before. The way that this works is that you use the background stars towards the center of our galaxy, which provide this incredibly detailed, essentially wallpaper. That's what you're measuring against. And the foreground stars with their planets move across that, and using the gravitational microlensing, enhance the light of the background stars to the bulge. So you want a place in the galaxy where there's a lot of stars that you could measure, because it's incredibly rare, because you have to have the right alignment. And so when the data comes to IPAC, it gets all of the time series data of all the stars gets measured and fit with models, and that's how we find the parameters of all of the exoplanets through microlensing. We should find a couple of thousands of those, not as many as we find with the transiting technique, but it provides a very unique data set to find the more distant planets than you can with a transiting technique, which is very good at finding planets that are very close into their stars.
Just real quick, that difference is really important for the understanding of how common habitable planets are. Almost all of our prior measurement techniques with other observatories, whether on the ground or in space, have a bias towards finding closer in planets. This microlensing technique is going to have a bias towards the larger separation planets, and the Goldilocks zone, the habitable zone, where it's not too hot, not too cold. It's not fully. Our survey of that isn't fully complete because of those biases towards the inner edge of the habitable zone. Roman's going to help us complete the outer edge of the habitable zone and complete that census, so we have a good understanding of how common not just planets are, but potentially habitable ones.
The technique is also really good at finding things like rogue planets that are just floating out there, or black holes that are just floating through space, because they bend the light and magnify the light exactly the same way as a star and a planet. They magnify the light of the background sources towards the center of the galaxy.
We have a question online from Isabella Mortar with Students for the Exploration and Development of Space. This is to Kristen. With no exclusive access period and most science running through the cloud via Roman Nexus instead of downloads, what does that change about who gets to make the first discovery in the data when nobody has a head start?
That's just one of the great things about Roman, is that it's sort of equal access to everyone. There is no proprietary period. There are no gates. Anybody and everyone can have access to the data, including students. In fact, we've set up data access not just for researchers, but a high school classroom can sign up for a team account on the cloud-based digital workspace and get access to Roman data. And we have tutorials and workflows for students to log on and be able to work on this as a group anywhere they want, on any school they want. So it's not. It's really about making sure that the data are not only accessible, like from a technical standpoint of logging and getting access to it, but that anyone that wants to can dig into the data and do the analysis right away. There is no hierarchy.
Let's go back to the far side of the room here. Yeah.
Thank you. Jackie Goddard for the Times of London. Nancy Grace Roman herself was a giant of astronomy, and her name is on this telescope, but I wondered as well to what extent the legacy of her work is written in the work that this will be doing. And also to Julie, I wondered if you could just sort of encapsulate the excitement of this on a personal level, what it means for you. Thank you.
Do you want to take both of those?
I can make it. I'll start with the second one. So, how excited am I feeling? I actually, I often have words, but I actually don't have words for that right now. It feels almost unbelievable to be surreal to be at the finish line. It's weird to, as we've completed building things and sort of handed the observatory to SpaceX for a launch, it's like there's this little pause before the storm. And I know that in a few weeks' time, we're going to be completely frantic getting things up and started. But right now, it's almost a sense of disbelief. I'm it's so extraordinary. I don't even have good words for it. But inside, I'm extremely happy. On Nancy Grace Roman herself, I told a story about the Coronagraph. So in the late 1959, she wrote a teeny tiny, smaller than you would be allowed now, article in Astrophysics Journal, where she hypothesized about the possibility of directly measuring planets in space. And so she wrote down the calculation, and she basically said, well, this would be really cool, and you could imagine an observatory that would do that, but it's clearly ridiculous. We're never going to be able to build observatories that are sufficiently stable and sufficiently sensitive. So I think if she was here now, she would really enjoy having been proved wrong.
Go to the room. Right here. Yeah, next to you. Right there, yeah.
Hi, excuse me, Will Robinson Smith with Spaceflight Now. Thank you all for the time. Question to Julie and potentially Kristen as well. Julie, you mentioned in a previous briefing that when asked, do you hope this will change our understanding of physics? You said, I'm paraphrasing here, I don't hope, I know it will. Do you feel like that will happen on the 5-year timescale that Roman is designed for its primary mission? Or given that it has enough fuel for 10 years, that once you hit that 5-year point, then you get to really start to finesse and do some weird things once you understand the particulars of the weirdness of the science and the physics that you'll have with the first 5 years of data? That all makes sense.
So I think the results from Roman are going to come in and in fits and bounds, and I'll answer, and then I'll let Christy get a word in edgeways. So when you first turn on a new observatory and you're we're going to open Roman's eyes and we're going to see the universe in a new way, and there are going to be things that we're going to discover simply because of that. So I think we can reasonably expect, I have no idea what they're going to be, but we can reasonably expect that we have a good chance of finding interesting things in the first few months, first year of the mission. The cosmology results are harder. They require exquisite precision. They require the large, ambitious surveys that we're doing. So the detailed results on how we're going to change our understanding of the universe itself, that's not going to happen until we're a few years later into the mission. So there's going to be sort of waves of an initial wave and then later waves of results coming out. And I think Kristen could add to this because we plan to have enhanced data releases where we process data to add extra value-added products to the data that I think will be a further sort of a general and jolt to the science. So maybe you...
Yeah, I think just to add a little bit to the general context that Julie gave, the science will roll out at different cadences depending upon how the observations are scheduled and what's available when. So, early on, we're going to be getting a season of observing where we can see the galactic bulge of our own galaxy. And so we'll be targeting that quite intensely for a couple of months, starting in February. And so right from the get-go, that first season of data, I think, will give us early results on exoplanets, on finding exoplanets, on the demographics of exoplanets. Some of the cosmology results require, a significantly more amount of data that will be accumulated over a couple of years of the first 5-year mission. And there's some really deep work that needs to happen on those data to control the uncertainties and the systematics in order to be able to get the very precise, it's a very hard measurement to make. So that might be on a little bit longer time scale within the 5 years. But there's also all sorts of astrophysics that's going to come out along the way that could change our understanding of the universe. And that can happen from any part of the surveys that were taken. My own personal science, part of my own personal science is to study some of the smallest galaxies in the universe, ones that are 1 million or 1 billion times smaller than our own Milky Way galaxy. These are the seeds or the building blocks of how we actually build up more massive systems like our own Milky Way. But many of them are just remain really, really tiny. They're small, they don't have a lot of stars, they're very hard to find. And so, I'm a galaxy hunter, if you will, looking for these small systems. And we've been looking for them with other surveys and finding them. But nothing will be like the Roman data will be for this work. And these galaxies are interesting not just because they tell you about how Milky Way systems form, they also are relics of structure formation in the early universe, giving us hints of the conditions in the early universe, how galaxies formed at all, and how dark matter and galaxies interact with each other. And some of those results from, just an example from my own scientific background, will be available likely in the first year. And that may give us hints of differences in how the early universe is working than we currently know. And so I think you're going to see results roll out in a wide range of astrophysics over time over the first 5 years. But there's also not just when the observations are scheduled, but as Julie alluded to, the data products that are available for scientists to use. The data comes down, this incredible deluge of data, and as I mentioned, we process that every single day and make products available every single day. But that is, we're using whatever calibration and algorithms we have at that moment to produce the best quality data we can. But over time, those calibrations get better, right? We're calibrating, initial calibrations of Roman during the commissioning period of the first 90 days after launch. And so we'll have a pretty good baseline of, how bright is that star actually, and how aligned do we need to make the telescope, the detectors to match each other astrometrically. But that improves the more time you have on sky. And so one would imagine as you get through the mission, you actually want to go back and reprocess all of the data, which, given the data volume of Roman, is a little bit of a daunting task, which is one of the reasons we've moved to be on the cloud, too, is that it allows you to do this very spiky, work on the data. And so every so often in a certain cadence, whether it's 6 months or a year, we'll reprocess the data from the different surveys and create richer data products, more uniformly processed and calibrated data products. And it's those that I think you'll see the data coming through, the discoveries coming through. When you get a data release and this type of additional work, you'll see a spike in results and discoveries and output, because it's these type of data products that really do help the community accelerate their work. You don't want scientists to have to do that individually over and over again on their own. It's way too complicated. And so when we release something like these data releases, I would anticipate there being big spikes in discovery and results.
Can I just add one thing to that, is that I think we're focused on these big questions that require exquisite calibration and large fields of view and large numbers. And because we're doing that, and because we're doing all this data reprocessing that Chrissy was talking about, that means along the way, all this other science that we didn't talk about, small galaxies and other things, can get done. They don't need this exquisite calibration. They may not need all of this data reprocessing that will appear along the way and towards the end of the 5-year mission. So that's why all of the science will happen. I'm particularly interested in how galaxies evolved. Every single galaxy, every single big galaxy in the local universe has an enormous black hole at its center. And the mass of the black hole and the mass of the stars in the galaxies have a tight correlation, and we have no idea how that comes about as galaxies grow. And I think science like that will come out of Roman because we're focusing so intently on answering these very, very big questions and processing the data so exquisitely that all this other science will come along all along the way between now and the end of the prime mission.
That is unfortunately all the time that we have for today. Thank you to everyone who participated and to our panel of Roman science experts. In 30 minutes, you can also join us on X and YouTube for the Roman pre-launch briefing. You can find our full Roman programming lineup and mission updates on nasa.gov/Roman. And then be sure to set your alarms early to watch live coverage of the Roman launch tomorrow, August 30th, beginning at 6:20 a.m. Eastern Time. Thank you and goodbye from NASA's Kennedy Space Center. Go NASA, go Falcon Heavy, and go Roman.